In this video, we will discuss the precise definition of a limit. I say the precise definition because we've already done an informal definition of a limit. So far, when we've been talking about limits, it's been very informal. And informal is great to help you understand the broad concepts, the big ideas. But informal is not very rigorous. It tends to be kind of touchy-feely. Calculus is one of the first higher level math classes, and as you go further with math, you kind of have to step away from being touchy-feely and start putting in the rigor. By that I mean you have to start getting into the nitty-gritty details about why things work, why things are true. This is our first attempt at getting into some of that. It may be a bit unfamiliar, maybe a bit challenging, but this is where we're going. Our learning objectives are fairly straightforward. First, know the precise epsilon-delta definition of a limit. Second, if you are given an epsilon value and the graph of a function, determine the corresponding delta value. That shouldn't make any sense without the definition and an explanation. Third, we will prove limits using the epsilon-delta definition. Specifically, if we're given an arbitrary epsilon value, we will have to figure out the corresponding delta value that goes with it. And fourth, do the same three things. Know and use the precise definitions for a one-sided limit and for infinite limits that balloon upward or downward to infinity. Now, first we got to start at our motivation. When we've discussed limits so far, we've had graphs that would look something along these lines, and we'd say, here's our x value of 3. When we've looked up at 3 and come over to the y-axis, we've seen a height of 2. So we've talked about as you start getting closer and closer and closer to 3, coming from the left and coming from the right, each one of these things is paired with y values, and we were paying attention to what happens with the y values as you start getting closer and closer and closer. As you pick x values that are very, very close to 3, what is happening to the y values up and down? Intuitively, that's a great way to think about the limits. And that's exactly the kind of things that they were doing back in the 1700s. When limits and calculus were really first invented, and there were a lot of mathematicians that were so excited about the power of calculus and all the really cool things it can do, that they just went flying through to get answers, and they didn't really take the time to make sure that they were really, really precisely correct. They were kind of a little bit informal with some of the pieces that they were doing, and the end result is there were little holes and gaps. There were tiny little things that were wrong in what they were doing. Then the 1800s came around, and you had an entire generation of mathematicians who said, wait a minute, we can't just play fast and loose. We can't be sloppy with mathematics like this. And so they spent decades going back to what the people had done before them and said, we're going to fix the holes. We're going to fix your mistakes. It was called the Age of Rigor. They spent a huge amount of time fixing the mistakes of what people did only 100 years before. 100 years before, their ideas were all correct, but they never got into the nitty-gritty details to really make sure that it was precise and certain correct. Oh, sorry, didn't bring that part up. Okay, the ideas behind these need to be formalized. Again, we've been talking as you start getting close on either side of our x value. Well, instead of saying either side of the x value, we want to have a tiny little window, a tiny little interval wrapped around our value. A little bit to the left, a little bit to the right. When we've been doing them, we were looking at pieces like 2.99, 3.01, where they took our number 3 and they did a plus small value and they did minus a small value. It was the same plus or minus on either little side. We were in some tiny little window. From there, we're going to say instead of going a bunch of values in a row, we can come straight up to the top and over, straight up to the top and over. You'll notice on our y-axis, this particular one isn't drawn to be perfectly balanced. A lot of times it won't be. We will have our value of 4 plus something, and we will have the value 4 minus something. This is kind of the big idea behind what we want to formalize. If we are given a value that says, I want this bound on the y, on the limit, the up and down, if I want it structured to be something small, like specifically, I want this to be 4.02 and 3.98. Well, if I'm doing that, I won't know right away what the x values are. If I pick the y values above and below the limit that I want them to reach, we will need to come down and figure out what are the left and right values. How close do we need to get to 3? And more generally, we're not just going to say things like 4.02. We could pick any plus or minus we want. We could have like 4.001, 3.999. What are the x values left and right of 3? Specifically, we're going to have 3 plus something and 3 minus something. We'll need to figure out what those somethings are. Let's look at a specific function to help us out with this idea a little bit more. Consider the function 2x plus 1, with the limit of that function as x is approaching 2. Well, we'll start off here. When x is approaching 2, what number is this limiting down on? Well, from the graph or from direct substitution, we should be able to identify the limit as 5. Here's a question though. If we are going to start getting super close to 5, for example, if I want to have it be 5.01 and I want to have it be 4.99. Well, let me back that up. I'm sorry. If I want them to be, I was getting ahead of myself. I'm going to use those numbers on the next one. If I want it to be 5.1 and 4.9, what are the x values coming down that are going to get me what I want? Well, here's the big idea behind it. I already have the y value of 4.9. I just said I'm going to pick 4.9. Which x value is going to get paired with that? Well, I can just go through and solve for this particular one and say minus 1, which will give me 3.9 equals 2x. Simply dividing by 2 then gives me 1.95 for my x value. That's what I will have to be on the left. Well, if I do the exact same thing on the right, 5.1 subtract 1, divide by 2, and I get some bounds on the left and right. If I want x values, or if I want to have the y value height of my function to be between 4.9 and 5.1, I am forced to pair it with x values that are between 1.95 and 2.05. Take the same problem, but instead of using 4.9 and 5.1, let's go more precise. Let's get even closer to 5. Well, same process. 4.99, we can figure out the x value that has to be paired with it. Subtract 1. Divide by 2. And do the same thing for the 5.1. Subtract, 5.01. Subtract 1, we'd get 4.01. Divide by 2, and we have 1.9952.005. Let's go even closer still. Instead of 4.99, how about 4.999? Get even closer. Well, what are the x values going to wind up being? You may have noticed a pattern developing. When we had a single 9, there was a single 9. And when we had 2 9s, there were 2 9s. It's actually going to keep doing that way. I'm skipping some of the algebra just to speed up the process a little bit. But because this one is 3 9s for this particular problem, I'm going to wind up with 1.9995 and 2.0005. The important thing to notice, though, is this right here. There is a relationship with the f of x. I'm taking f of x, the 5, that was our limit value. We're taking the 5 and adding some small value and subtracting some small value. Using those small values, I'm able to predict what the x values are that are going to go with them. When we look at the formal definition of a limit, this piece of considering the size of the plus minus and using it to predict a plus minus in the x values is going to play a role. We will see that role further. The biggest idea behind the process of a limit is we will determine the bands above and below the limit that we want to start with. How close do you want to be? Do you want to be within 0.1, 0.01, 0.05, 0.0001? You pick how close you want to be. Your upper bound is going to be 5 plus that amount, called epsilon. The lower one will be 5 minus epsilon. Those will be paired, dropping straight down with values along the x-axis. It's going to be to the left and to the right of what we're limiting on. The piece to the right is also a plus, but we are going to use the letter delta. The piece on the left is 2 minus that delta. And so when we pick a plus or minus on the 5 for the limit, we will need to figure out the plus or minus on the 2 for the y-axis. What the number is for this delta, that's what we will need to figure out. After we figure out the delta value, we'll be able to write up the details and actually answer the question. Here is the actual definition of a limit. I cannot stress enough how incredibly important this piece is. If you're taking notes, and you should be, pause the video, copy this piece, memorize it. There is a lot of information here. It's really, really, really important that you know it. Now that you have the video or the piece copied, let's go back and relate this piece to what we were just discussing. F of x is our function. L is the limit. In this back problem, we were looking at here's our limit of L. When we go 5 plus epsilon and 5 minus epsilon, that's actually based on the function value here of f of x and here of f of x. What we're looking at doing is taking f of x plus minus something. Writing it out this way with the plus minus, though, is a little bit sloppy, a little bit imprecise. But that's the major idea behind what absolute value does. This piece, when we put down the absolute value, is saying away from the limit value of L, which in our last example was 5, you can go up or down, but the how far up or down you go has to be less than some number that we've picked in advance. Same component over here. The part that we are limiting on, you'll notice this says the limit as x is approaching a. This is what our limit is going toward. Here, this is saying the limit is approaching a 2. Well, we had 2 plus on the right, 2 minus for the left, but that's what this piece is saying. If we want to know how far away from this number we're limiting on, and the last one it was 2, we can take the distance with the absolute value, but it's got to be less than the plus minus delta component. Perhaps the best way of actually seeing this is with some examples. So here is our first problem. Use a graph to find a number delta such that if absolute value of x minus 1 is less than delta, then the absolute value of the function x squared plus 3x minus 2 away from 2 is less than 0.2. Another way of rewriting this, we're taking the limit as x approaches 1. Here's our x approaching a 1. That's going to be a limit of the function, and this whole piece is our function. That should be closing down on a 2. That's our limit value. In order to show that this is true, I've picked a specific epsilon value and said, based on this epsilon value, tell me the number for the delta. We need to know that information. In order to get this one, we're using a graph. Now, I have it set up where I've already started putting this piece into my TI nspire. You'll note the graph is already, the function is already graphed. If you're using a different calculator, by all means, pause the video, get it typed in. If you're using nspire, pause the video, get it typed in. But we'll continue here. The major feature that we're noting is our distance is away from 2. The distance up or below is here. So we can be 2 up, or we can be 2 down, or 0.2 up, 0.2 down, away from our limit value. Those are pieces that I am going to graph into the calculator. So menu, graph entry, add another graph function. And so I'll take 2 plus 0.2. Enter, and you can see it has drawn my upper bound, my horizontal line, a little bit above my 2. I also learned that you can press the tab button to enter a new function, so I'll go tab, save some time from going through the menu, and go to subtract 0.2, and click enter. And you'll see it's given me a graph that's a little bit below 2. Well, I don't care about the entire graph. The only area we're concerned about is this tiny little region over by 1, because we're looking at the limit of 1. So I'm going to go menu and zoom in. And we're zooming in. You'll have to use your arrow key to scroll around, but we're going to zoom in here and zoom in more and zoom in more and zoom in more. So we can see from the graph now, the blue is my function. The red is my upper bound, 2 plus epsilon. The bottom is 2 minus my epsilon that I've picked. I need to know what are the x values where they're crossing the graph. And to do that, I'm going to use Analyze Graph and use the intersection feature. Now for the intersection feature, you'll notice in the bottom left it asks for graph. You can use the arrow key To scroll over, you can use the scroll bar, but we have to go select F1, press enter. It asks for the second graph. So what is the other piece that it's going to intersect? Well, again, you can scroll up, but you've got to scroll up to our F2 and select it. Now it asks for a lower bound. The lower bound has to be on the left side of where they cross. You'll note this one already is, so I can click enter. Now it asks for an upper bound, so I can use my arrow key and start scrolling over until I'm past where they're crossing and click enter. Now do you see the point of intersection? It tells me it's crossing at the point 1.04, 2.2. It's giving me the x value for the point of intersection. I will have to repeat that entire process for the lower line now. And I'll go through it more quickly here. Menu, analyze graph, intersection. Pick my function, pick my other line. I have the lower bound, I have the upper bound. It's given me the intersection. So what this is telling me, do you see the x values of our coordinates? 1.04, 0.96. That's telling me the x values for this are going 0.96, are between my x value for the 1 and up to 1.04. This 0.96 is the x value that comes from having 2 minus epsilon. This is the one that comes from 2 plus epsilon. These are the x values that are getting associated with it. Well, my x is 1, so I need 1 plus delta, 1 minus delta. What is my delta value? Well, in this one, we should be able to see we have delta is 0.04 because it's 1 minus 0.04 or 1 plus 0.04. By that, though, we've got to be a little bit careful because the calculator is not giving us exact values. It is giving us rounded, approximate values because they don't want to go through and give you like 20 correct digits for the number. They've rounded it. It's possible that this 1.04 could actually be a number like 1.0447, in which case it has rounded downward to 1.04. And it is possible that 0.96 could actually be something like 0.9571, in which case it's rounded upward to 0.96. Either way, to give us some wiggle room on potential rounding, instead of picking a delta of 0.04, if we pick a delta of 0.05, we know that we're outside that possible range for rounding error. And so that's our answer. Use the graph to find a number delta such that this stuff checks out. And our graph does that. This is telling us on this particular graph, if I take any value, because my graph is looking like this. Here's 1. If I pick anything from 0.95 up to 1.05 and then come over to the y-axis, well, we know this one's at 2. All of these numbers, all of these values are going to fall inside 2.02 and 1.98. It's a guarantee. All of them will fall in between these two values. That's what the precise definition of a limit guarantees us. Here's our second example. And perhaps, arguably, one of the most important in the whole piece. Prove that the limit as x approaches -2 for the function 5x minus 1 equals 9. Now, based on the direct substitution part, we've already done pieces like 5 times 2 minus 1. hey, it's equal to 9, and we already have a piece that gives us answer based on theorems. The theorems were not proven. The theorems, without the proof, are kind of touchy-feely. It's saying, well, this is true, just believe me. Well, just believe me is not very nice in math. Prove it to me. Make sure that you have a knockout explanation that people can't argue with. Here's our process. If we go back to the limit definition, it starts off by saying, if we have this piece is true. If we start off by saying x minus 2, and we're picking 2 because it's what we're approaching. If we know that this is less than delta for a positive number delta, then we need f of x minus the limit to be less than a number epsilon. But epsilon can be anything. It can be 0.01. It can be 0.000001. We could pick an epsilon that's 0.00000, do 100 trillion zeros, and say, make it closer than that. Or put in a Google number of zeros, or a Googleplex number of zeros. Put in as many zeros as you possibly can, and still figure out a delta that's going to make it closer than that. This is the part, this piece of absolute value, we need to figure out. The idea behind this is similar to solving equations. Since this piece in red is what we need, we're going to start there and work our way backwards. We'll work our way backwards trying to get to the if statement. And once we work our way backwards, we should be able to come upon a point where we can make a substitution, get the answer, and then over on the left-hand side, we'll write up the details, completely filling in the rest. So here's what we've got. Our function, f of x, is 5x minus 1. The L value that it's limiting down on is 9. So we need this part for an epsilon. Well, let's do some work on this piece. What is 5x minus 1 minus 9? Specifically, what's negative 1 minus 9? Those pieces will combine to give us 5x minus 10. Do you see anything we can do with that, with the numbers in our expression inside the absolute value? Well, we can factor out the 5, which leaves behind x minus 2. And again, this is what we need. But because we have a positive 5, we can actually factor out and pull out this positive 5 outside the absolute value, and we get this piece. You notice the absolute value is of x minus 2, matching up what we had assumed we already had. That's not an accident. If we were to go through and divide this bottom inequality by 5, that would tell us x minus 2 is less than epsilon over 5. But that's kind of what we were trying to get. We were trying to figure out what delta value are we supposed to have, because we don't know what delta is. Well, why don't we call that one delta? After working backwards, we can then say, let's take the delta that's equal to epsilon over 5. That way, if somebody wants to pick epsilon that's 0.00002, all we have to do is take whatever epsilon they give us, divide it by 5, and we will have the number that's going to give us what we want. It'll give us our delta value that we want. Okay, all of the stuff on the right-hand side, that was scratch work. I'm changing the color to purple so that we can start writing up the details. let epsilon be some number that's greater than 0. If we have 0 less than x minus 2 for absolute value is less than delta equals epsilon over 5, then we're pretty much going to start at the same point now of over here and start working our way downward. F of x minus L, which is 5x minus 1 minus 9, which is equal to 5x minus 10, which is equal to 5x minus 2, which is equal to 5 times the absolute value of x minus 2. This piece, I claim, is less than 5 delta. Why does that have to be true? This is one of the parts that sometimes trip people up. They're not sure, why is it that we can change it from equals 5 absolute value into less than 5 delta? Well, to help explain that a little bit better, I'm going to make up some new numbers that are completely and totally unrelated to this problem, and I'm actually going to write them up in yellow just so that you can understand why that step is true. Suppose that we had a piece like right here that's 5 times 3. And back up at the original, you'll note I'm basically saying absolute value of x minus 2 is like some number 3. If I was saying back up here, 3 is less than the number 4, well, you'll buy that. 3 is less than 4. And then I come down at the bottom and say, down here I have 5 times 3. Because 3 is smaller than 4, if I replace a 3 with a number that's bigger than it, like 4, shouldn't 5 times 3 be smaller than 5 times 4? That's what we're doing. When you substitute a smaller number for a number that is greater than it, you change it from an equality into a less than inequality. When we substitute it in this particular method. That's all we're doing. We're taking a piece where we replace x minus 2, absolute value, with the bigger number delta down at the bottom. It's just like replacing 3 with 4 to get something that's bigger than it. All right, so continuing our problem, I'm switching back to purple. Hopefully that explanation made sense. Well, this is 5 times delta. We said back up at the top, though, delta equals epsilon over 5. So substituting in the equality, that's epsilon over 5. Well, we have multiply by 5 times 5. Those cancel, and we get equals an epsilon. No matter what number they give us, if we take the number and divide by 5, we can get closer on the x-axis than we want, as close as we want. This whole part in the purple is the write-up. It's the solution for this particular problem. All the stuff in the red and the blue on the right-hand side, that was scratch work that helps us be able to write up the answer in purple. Now the same idea applies for one-sided limits. You'll note our definition for a left-handed limit, we're taking the limit as x is approaching a from the left. That's like saying all the stuff where we're doing 3 plus delta, we don't care about that. All we care about is doing the 3 minus delta. And that's exactly what this piece is saying right here. It's using the letter A instead of using the number 3, but it's just saying the x value, subtract something to the left. This is giving us our window of 3 minus d over to 3. This piece is saying a minus delta over to a. It just happens that we're using an a of 3. Okay, if we pair those together, we are still going to come straight up from our a minus delta to get something like 7 minus an epsilon. That's the limit. Depending on the type of graph, though, this one winds up being that the graph is falling underneath our limit of 7. If we had a decreasing function like this line, when we came up, we'd have to go above it and come over. Or let me redraw this so that it fits better. Here's our line. In this instance, when I come up from 3 and hit the graph and come over, I'm actually getting something that's a little bit above 7. The whole reason that we have this absolute value in play is so that we would have the possibility that if we have a function, it might wind up being that when we come straight up, it might be underneath the limit, or when we come straight up, it might be above the limit. We don't know which one it's going to be. So we put in the idea of an absolute value just so we can cover the bases. Where it intersects, it might be below, it might be above. We don't know, it just depends on what the graph is going to look like. But it's that same idea. If you pick any epsilon value you want, so we go above or below, if you get within this range above or below the limit, I am forced to figure out how close we have to get to the x value, in this instance 3. Well, it's the same idea if I'm saying get really close on the left-hand side, or if we're saying get really close on the right-hand side. This idea of really close is still based on the epsilon-delta definition. We'll take advantage and use this in a second. So here, use the definition to prove that the limit of square root of x as x approaches 0 from the right is equal to 0. Well, first off, why aren't we doing a total limit? Why do only a limit from the right-hand side? Well, can you actually approach x from the left? If you're approaching 0 from the left-hand side, that means you're plugging in numbers like -1, or -1/2, or -0.001. You can't take the square root of a negative in the real numbers. We don't work with the complex number I. We are forced to do a one-sided limit because the left-hand limit doesn't make any sense. It's outside the domain of the function. Okay, now when we're backtracking, we're going to take advantage of this one. We're using a right-handed limit, so we are going to use the definition for a right-handed limit. Remember that we're setting up scratch work on the right-hand side before we come back to the left and rewrite it. So here's what we're looking at. If we have a is less than an x, which is less than a plus delta. Backtracking again, that's exactly what we had here. We will need to figure out what the delta value is. Well, first off, remember, a is what the limit is approaching to. It's approaching 0. This a is the number 0. So what we really have going on is saying, whoa, that was too big. If we have, whoa, it's erasing everything on, okay, the board wants to erase everything on me, I'll just have to rewrite it. So if we have 0 is less than x, which is less than 0 plus delta, we are going to have to figure out what that delta value is. Then the part that we need to be true is based right over here. It's the same f of x absolute value stuff that we had before. F of x minus the limit has to be less than any epsilon value we are given. Let's start putting the pieces in. F of x, oh, sorry, I didn't want the f, is just the square root of x. L is the limit. That's another 0. We need this part to be true. Well, of course, subtracting 0 doesn't do much. It just says right there. Well, one thing to keep in mind now, absolute value of a square root. Square roots are already positive. When we use the square root symbol like this, it means the positive square root. So we already have positive numbers. We don't need the absolute value because the square root alone already gives us positives. Remember, we are trying to get to a point where we're saying we need x by itself. So let's consider what we need to do. If we go through and square both sides, square and square root cancel, and we get x is less than epsilon squared. Why don't we just take delta equals epsilon squared? If this is our delta value, we're all set. So let's just call delta epsilon squared. And there we go. That whole part, all the stuff that we were doing on the right-hand side, was just to figure out this one thing. What does delta have to equal? Now that we know delta would need to be an epsilon squared, we can go back and write up the details like in our definition of a limit, a right-hand limit. Take any epsilon you want that's greater than 0. If we start with the assumption that 0 is less than x, which is less than delta, equal to an epsilon squared, then absolute value of f of x minus L, which we need to be less than an epsilon that we're given, that part is equal to the square root of x minus 0, which is equal to just the absolute value of square root of x, which is equal to the square root of x, which is then making our substitution. That part is telling us that the square root of x is less than the square root of delta, which is actually just following from this part where we take a square root of both sides. Because this part is true, when we square both sides, this tells us x is less than delta square root, but delta is equal to epsilon squared. Just making that direct substitution. Square and square root cancel, giving us just epsilon. And that's exactly what we needed to show. If we start with this assumption, using the delta equals epsilon squared allows us to run through some algebra and show this piece is less than the epsilon. That's what we needed. All the stuff that we had written on the blue on the left-hand side, that's our work. The right-hand side is scratch work, but the left is our answer. Now, total limit. Use the definition to prove that the limit of x squared as x approaches 4 is equal to 16. Please note we're doing a total limit, which tells us we are using the original definition. If this absolute value is true. Come on, where's my problem? If we start by assuming 0 is less than or equal to x minus 4, again, 4 because that's what the limit is approaching, is less than or equal to some delta, which is equal to something we need to figure out. We need absolute value of f of x minus L to be less than an epsilon. Let's start checking through what we have. So what we need, x squared is our f, L is this piece for 16. We need this. You see how it can be factored? X squared minus 16 is x squared minus 4 squared. So we can use the difference of squares formula and say x plus 2 times x minus 2 using the triangle inequality, we can split this part up and note that we have x plus 2 times x minus 2. Actually, I should rephrase, it wasn't the triangle inequality, but this is the part that we need to be true. Please note back up at the beginning, why did I get the 2's? I'm sorry, I did something foolish. I looked at this 4 for the 4 squared, and I took the square root of 4 to get these 2's down here. I shouldn't have. I'm sorry, I just did something silly. I was supposed to take the square root of the 16, and my brain just got dumb for a second. I'm sorry I made that error, but we've got to backtrack and note that these are not supposed to be 2's. They are supposed to be 4's, so let me erase these 2's and fix my mistake. Fix my brain fart. X, oh, I also wrote a 2 again. X plus 4, x minus 4, and here's what we have. Okay, so coming back up then, you notice how we have this piece that's absolute value of x minus 4 right here. Please notice that's like what we had back up at the top. However, down here at the bottom, we have another issue where we've got this other absolute value part. This is the problem that we're going to run into. When we did our linear one back in example number 1, when we got to, example number 2, it wasn't example 1. When we got to that point, we had a constant number 5. Now, we don't have a constant like the number 5. We have a we actually have something that's still involving the x. What we would like to be able to do is somehow make a substitution so that we can replace the absolute value of x plus 4 with some constant number, and we would say like a c. Because if we could somehow replace this with a c, then we could just divide over and have epsilon over c, just like we were doing back in problem number 2. In order to do that substitution, though, we're going to have a little bit more algebra that we're going to have to work through. One of the things to keep in mind, of course, that when we're doing the epsilon-delta definition, remember, we are only concerned with functions that are concentered, or rather, we're only concerned with x values that are right near our 4. If we were all the way over here at 4, we just need to have our little neighborhood, our little open interval on either side. We don't care about finding something that restricts all of them. We only care about this one small little area centered around a 4. Well, an easy one to be able to say then is let's consider all the x values that are centered around the 4 that we care about, but the distance away from them is only going to be a 1. please note this part that I've written down in the red is saying the only ones that we care about are the x values that go from 4, not 4, that go from 1 to the left and 1 to the right. I just rewrote that absolute value. The only x values we're caring about are a little bit to the left, a little bit to the right, and specifically within 1. So if we are considering x is between 3 and 4, let's consider x plus 4. What does x plus 4 have to be bounded within? We'll add 4 on the left, add 4 on the right, and we have this piece is bounded between 7 and 9. So that's telling us this piece right here, the absolute value of x plus 4 in the interval we care about, not everywhere, but only in the area of interest to us, that tells us this is a piece that is less than 9. That is interesting to us because it does the same type of problem like we had done before. Remember when we had done a substitution where we took delta and replaced it, or we took an absolute value and replaced it with the delta that was bigger than it, and it was less than? Well, this piece that we have, where we need x plus 4 times x minus 4, if we do the substitution, because this piece is less than 9, this has to be less than 9 times the absolute value of x minus 4. So we have this whole piece, and I'm going to grab my, whoa, too big, too much erasing. I'm going to grab this whole piece and slide it over so I have more room. We need then this piece to be less than an epsilon. Well, looking at the green, why don't we just divide by 9? That cancels, and we can call this number delta. By picking this delta, we can put the entire chain together that says absolute value x plus 4 times absolute value x minus 4 is less than epsilon over 9, which is our delta value. Strictly speaking, we did introduce another restriction. We said we needed to have, back up here, that the distance away for this x minus 4 has to be less than 1. This also said, here's another delta. So strictly speaking, what we've done is take delta 1 and take delta 2. We actually have two different deltas because we've put in two restrictions. The delta we use is going to be the smaller of 1 and epsilon over 9, which generally speaking, unless somebody's picking an epsilon value of 10, which is kind of silly, you just wouldn't do that. We're going to have it be epsilon over 9 pretty much whenever we're doing it. So we'll come back and say delta is equal to epsilon over 9. So yeah, a crap load, a lot of scratch work for this particular one because, well, frankly, squares are more difficult to work with than lines. You know, just no way around it. It's just tougher algebra. But the good news is we were able to figure out the delta definition. All our scratch work is done, so we can switch over to purple and now say, take any epsilon you want that's bigger than 0. And if we have 0 less than or equal to x minus 4 absolute value is less than delta, which was equal to the smaller one of 1 or epsilon over 9, then we'll run through our part for our f of x. F of x minus L, that part is equal to absolute value x squared minus 16. And cutting out some of the algebraic steps, we would recognize that's equal to x plus 4 times x minus 4, which has to be less than 9 times absolute value of x minus 4. And just to help people understand what we're doing, I'm going to put in a little note, because absolute value of x plus 4 is less than 9 on 3 less than x less than 5. Just putting in that little note, so if somebody's reading it, it helps them understand where the 9 came from. Because otherwise you just look at it and say, wait a minute, that 9 just seemed to pop up out of nowhere. We'll put in this note from our scratch work that gives a quick little explanation of where the 9 came from. It just makes it easier for other people to read and other people to understand. All right, so from there, we'll continue and make another substitution, which is less than 9 times delta. And just in case people aren't sure why that part's true, we can put in the comment, because absolute value of x minus 4 is less than delta by the assumption. Just makes it easier for other people to understand why you are correct. And switching back to purple, which is equal to 9 times epsilon over 9, which is equal to epsilon. And there we're done. All the purple on the left-hand side mixed with our little comments to help the reader understand in the red, that is our solution. All the black and yellow and some of the red on the right side and the green, all that other stuff was just scratch work to help us get to the formal, precise write-up that we have in purple. Continuing. This idea of an epsilon-delta definition is used when you have limits that balloon upward to infinity. But we do have to tweak it. And here's our reason why. When we were talking before about saying, here's my limit, and I could go plus or minus an epsilon value, well, this is saying it's a limit that goes up to infinity. So you tell me what infinity plus or minus epsilon looks like. Infinity plus or minus epsilon really doesn't make sense. So in this instance, on our left and right hand side, that completely makes sense. We can still talk about a delta value on the left, a delta value on the right. That part's still the same. The part that doesn't make sense is plus or minus epsilon. Instead of saying getting plus or minus epsilon or getting really, really close, you should remember that the idea behind an infinite limit is that you can pick any positive number you want. You want to pick 1,000,000? Show me that the function gets up bigger than 1,000,000. You want to pick 100 trillion? Show me that the function gets up higher than 100 trillion. You want to pick 1 followed by 52 pages of 9s? Show me that it gets up higher than that number. That's what this piece is saying. M can be any number you want. Imagine any number you want that's really, really, really huge. And if you can show that the function goes up higher than any huge finite number, that's telling us it's going upward to infinity, which is what this piece is telling us. In order to use it, we'll bounce back to this one in a second. Feel free to pause the video. But we're going to look at problems like this. Use the definition to prove that 1 over x to the 4th, as x approaches 0, balloons upward to positive infinity. Please remember the graph for this, and since this is scratch work, I should put it off to the side here. The graph for this looks like a flattened out parabola. this is the graph for x to the fourth. Well, when you start dividing by numbers that are less than that, the graph will be altered. Instead of having 1 over, when you start taking and dividing by 1 over, the graph is going to look like this. So we can see as you start approaching x from the left and from the right, it is going upward toward infinity. But we need to be able to explain that. And I want to get rid of that purple, because that's just bugging me right now. I'll get rid of that and get rid of this piece. But there we go. Here's our graph of 1 over x to the fourth. Okay, so we'll put this piece down and say, let's get started. Our assumption, if, and let's go back and take a look at it. Same type that we had before. 0 is less than or equal to x minus the a value. In this instance, it's 0. Is less than delta equal to, we will have to figure it out. Then, what we need is f of x to be bigger than any finite m value we want. This is what we need. So, since this is what we need, let's go and plug it in. 1 over x to the fourth is greater than m. Well, of course, m is a number, so we can put it over 1 to create a fraction. And one of the algebraic properties that we can take advantage of is we have a pair of fractions based on an inequality. If we take the reciprocals of both fractions, flipping them, it's actually going to change it to be less than, which we would then note tells us x to the fourth is less than 1 over this finite number m. Taking the fourth root of both sides, we would get x is less than 1 over the fourth root of m. But because 4 is an even number, this is actually taking an even-powered root. It's not just x to the fourth. It's not, let me rephrase, it's not just x. Because we are taking an even-powered root, this could actually be positive or negative x, because this refers to only the positive root. Well, since we have the possibility that we have plus or minus, we can take care of the plus or minus just by saying, ta-da, now it's strictly positive. Please note, back where we were up at the beginning though, the absolute value of x minus 0 is just the absolute value of x. It needs to be less than delta, but we've just found a delta value that will work. It needs to be a delta value of 1 over the fourth root of the m value. And here's our scratch work, all the stuff on the right. Not quite so bad as it was last time, right? So, let's get our right up in purple now. For any 0 less than m less than infinity, so for any positive number n, m, I said n, I'm sorry. Or rather, instead of saying for any, I prefer to use the word take. It's comfortable. I like writing it that one. I could have continued with it, but this feels more comfortable for the way I'm writing them up today. If we start off with the assumption 0 less than or equal to absolute value x minus 0, which is the absolute value of x, that's less than delta, which we have chosen to be the fourth root of whatever number m we're given, then f of x, which is equal to 1 over x to the fourth, which is equal to 1 over the absolute value of x to the fourth. And you'll note I can say that because a fourth power is guaranteed to be positive. If you multiplied 4 negatives, you get a positive number. If you multiply 4 positives, you get a positive. So either way, I can put in these absolute values and not change it because it's an even-powered exponent. An odd-powered exponent, we wouldn't necessarily be able to say that. Anyhow, this number has to be greater than 1 over 4 root to the fourth, which is equal to, I wrote that backward, I'm sorry. This piece has to be, where's my color? This is a number that has to be greater than m. And our reason for that, because 1 over absolute value of x to the fourth, we would be able to say is greater than 1 over delta to the fourth. We can say that because this is a less than, because it's a less than, if we took the reciprocal 1 over, we know that would force us to actually switch this piece. We'd have to switch the inequality with the reciprocals, which is how we get our 1 over. Okay, so we'd have that's greater than 1 over delta to the fourth, which is equal to 1 over, and delta was 1 over the fourth root of m to the fourth, which equals 1 over m, and 1 over m is just m. Kind of some tricky algebra there, a little bit weird to sort through, but here's some extra scratch work to help people see why this particular statement is true. But we've hit the important part. We have shown if the first part is assumed, then we can follow through logic and show f of x is greater than any m value that we are given. Oh, I'm sorry. I went backwards on that one. I hit the wrong button. F of x is greater than m. The similar process would actually work if we had a graph that was falling down to negative infinity, like 1 over negative x to the fourth. If we had a graph like that, or 1 over negative x squared. If we had graphs like this that fall downward toward negative infinity, instead of saying they must be higher than some positive number n, they have to go lower than some number, and we just change the letter to be n just because we'd like to use a different letter. But the ideas and the concepts are still the same. If you're doing an infinite limit, you will need to start off with the assumption and then start playing with the piece that you need. In order to use the definition, it's saying, here's the part that you are given for free, and to use the definition, this is the part that you need. So start by assuming the given, and play around trying to get the part that you need, where we're going to work backwards and deconstruct the problem. Sometimes the algebra is easy, sometimes the algebra is more complex, but we will need to do the work to deconstruct and work our way backwards so that we can figure out what the delta value is that's going to make it all come together. Once we've got the delta value that makes it all come together, we will go through, plug it in, and start working our way through the definition to finish off the rest of it. That's our work for today. For the precise definition of a limit, there are a couple things that you should know. Memorize that definition. You're going to need to work with it. It would also be very beneficial if you had memorized and you could write up the definition for a one-sided limit and for infinite limits. One of the pieces that's going to be very beneficial if you're working with graphs, especially because graphing calculators are so incredibly powerful, if you have a specific epsilon value that you need to reach, figure out the delta value. That particular learning objective is most beneficial when you are working with engineering problems. For example, an engineering problem might tell you the diameter of a crankshaft has to be within a certain tolerance, yet you can't get it to be too far out of circular. It's used a lot in automotive, it's used a lot in engineering. Third learning objective. If you're given an arbitrary epsilon, so instead of a specific number epsilon, an arbitrary just variable epsilon, figure out the delta value that will work for it. That's the whole scratch work stuff that we were doing. And finally, know and use the precise definitions for both one-sided and infinite limits. The process is the same on all of them. Start off with this piece. Where is it? Where is it? Where is it? Come on. Where is it? Where is it? Start off with the piece that you are given that we assume is true, and then with your scratch work, figure out how to make the stuff that we need to be true, figure out how to make it true. Work backwards until you can isolate your delta. All of those things together will help you learn the learning objectives for the precise definition of a limit.